All right, today is 4.3a. And starting off with a graph. Should look like this. And I want this point to be at x equals 2. I want this point to be at x equals 3. And it looks like that's at 5, maybe. So the topic for today is we're going to shift gears. The last couple days we've been talking about when the graph of f is going up and when it's going down. Now today we're going to talk about when it's cupped up. So it's talking about the curvature and when it's cupped down. So from 0 to 3, the graph here is cupped down. So that's called concave down. So this is f of x. So f of x is concave down on 0, 3. And then it's cupped up from 3 to infinity. So it's concave up from 3 to infinity. And then the point where it switches from concave down to concave up, or vice versa, so that's right here, that's called an inflection point. So there is an inflection point at x equals 3. So we're totally shifting gears here. We're not talking about going up or going down. We're talking about cupped up or cupped down, concave up, concave down. So there's a lot of different possibilities. That is going up, so it's increasing, and it's concave down. On the other hand, this is concave up, going down. So, going up, concave down. Going down, concave up. Or it could be, there's two more possibilities, and sometimes I get lost. Could be like this. Could be going down, concave down. Or you could have a different graph that was going up, concave up. So there's 4 possibilities. Because you can either be concave up or concave down, and you can either be going down or going up. So those are the 4 possible shapes. But I just want to make sure you know that when I'm saying concave down, it doesn't have to be the full cup. It could just be half of it, right? Okay, so now let's think about this. These two are concave down. So the slope starts out pretty big. But then the slope becomes less. Then over here, the slope is a small negative, and then it's a larger negative. So in both scenarios, the slope is ending up less than it was. Big positive, smaller positive. So the slope is becoming less. And here's a small negative and a big negative. So the slope is becoming less. So when a graph is concave down, the slope is decreasing. When the graph is concave down, the slope is decreasing. So again, what I mean by that is big positive, smaller slope. Big negative, or sorry, small negative, smaller slope, because now it's a bigger negative. So this is kind of interesting because it's talking about the change of the slope. So it's talking about how the slope is changing, which would be the derivative of the slope. The change of the slope is the derivative of the slope. So if the slope is decreasing, that means that f double prime is negative. Okay, so that brings us to something called the concavity test. So the concavity test says that if f double prime is negative on an interval, then f is concave down on that same interval. If f double prime is negative on an interval, then f is concave down on that same interval. And then it also turns out that if f double prime is positive on an interval, then f is concave up on that same interval. So let's try a problem. This is going to be f of x equals e to the negative x squared. And we're going to find the intervals of concavity. And identify any inflection points. Okay, so if we're going to find the intervals of concavity, we need to find the second derivative. Because according to the concavity test, we have to figure out when the second derivative is negative and when the second derivative is positive. So when the second derivative is negative, that's where it's going to be concave down. And when the second derivative is positive, that's where it's going to be concave up. All right, so first of all, we need to get to the second derivative of this. Well, before we can find the second derivative, we need the first derivative. So we've got e to a mess here. So that's a chain rule problem. The outside function is e to the x, and then negative x squared is plugged into it. So the derivative of the outside is e to the x. But then you have to plug the regular inside into that. And then to finish out the chain rule, you multiply by the derivative of the inside. So you have to figure out the derivative of negative x squared. That's negative 2x. So there's the first derivative. E's always bother people. Is everybody okay with that first derivative? I would probably put the negative in front, so negative 2x e to the negative x squared. Yeah?
So you did multiply by the natural log of e, which is just
Sure, I did.
just
But for me, so yeah, you're right. The general rule for a number to a letter is the natural log of the number times the number to the letter. So yeah, you could do it that way. But in my mind, I just know that separately the derivative of e to the x is e to the x. So I use it as two different memorized things. But it's fine if you do it that way, and it works out the same because the natural log of e is 1. Good. Yeah. But that's why I didn't talk about it, because in my mind it's a separate thing. But they are related, you're right. Good. Okay, so here's the first derivative. So now we need the second derivative. But keep in mind that if the question said find the increase-decrease intervals, we would work with this, right? That's what you did last night. You found the first derivative and figured out when it was positive. That was to figure out when the f of x function was increasing. But now, since we want to know the concavity, that's why we have to find the second derivative. Okay, so for the second derivative, it's a product rule. So you take the derivative of the first thing times the regular second thing plus derivative of the second thing, which is that chain rule that we did just a minute ago. There's the derivative of the second thing times the regular first thing. So derivative of the first thing times regular second thing plus derivative of the second times regular first. Cleaning that up, it would be negative 2e to the negative x squared plus 4x squared e to the negative x squared. So we need to figure out, now that we have the second derivative, before I go on, is everybody okay with the second derivative? Okay, so according to the concavity test, we need to figure out when that second derivative is positive, and also when it's negative. So now we're going to solve that inequality. 2e to the negative x squared plus 4x squared e to the negative x squared bigger than 0. So now it's just an inequality. So this is why I've been harping on inequalities so much the last week. This is just a regular old inequality. This mess that I'm pointing to happens to be the second derivative, but that doesn't change how we're going to solve the inequality. It's just an inequality. So how do you solve an inequality? You have to figure out when the mess is equal to 0 and also when the mess is undefined, right? Because that's where the mess might switch. So anytime you're solving an inequality, you're going to find the possible switching places. Yes? We have to do both because we're trying to find out when the second derivative is negative and also when the second derivative is positive. So I just chose to do this one first. But you're right, I could have chosen the less than 0 just as easily to do that one first. Good. All right, so to figure out when this mess is bigger than 0, I have to find the possible switching places when that, and that's when this mess is 0 or when this mess is undefined. Did I miscopy something? Just this right here should be negative. Thank you very much. I appreciate it. Is everybody seeing that? I just transferred a +2 over here that should have been negative. All right, cool. So I got to figure out when that equals 0, and I've also got to figure out when that is undefined. So this is looking familiar. We've done this a lot in the last few days. Figured out when something was 0 and figured out when something was undefined. And it's just because those are the possible switching places. Okay, now yesterday, this mess that we were working with happened to be the first derivative, right? So there's a special name for when the first derivative is 0 and the first derivative is undefined. What's that special name? Critical values, right? But this is the second derivative equal to 0, and the second derivative equal to undefined. So the points we're going to get, they're not going to be called critical values. That's a special name just for the first derivative. But they're going to be important values. They're going to be potential switching places for the second derivative. All right, so let's solve this. I'm going to pull out the e to the negative x squared and also a -2. So that'll be 1 minus, I pulled everything out of here, so 1 is left over. And then 2x squared. So then I can put that downstairs, and it'll make the exponent positive. Yes. When you have e to a negative power, that's 1 over e to the positive power. So if you have e to a negative x squared, that's 1 over e to the positive x squared. Good. All right, so I'm trying to figure out when this is 0, and a fraction equals 0 when the top is 0. So I just have to set this top equal to 0. So then you divide the -2 to the other side. It'll be 1 minus 2x squared equals 0. Then you subtract the 1. Divide the -2. Take the square root. Don't forget, when you take a square root, you get 2 answers, right? Like if this was 4, the answers would be both positive and -2. So since it's a half, it's positive and negative square root of a half. So there's 2 possible switching places for the second derivative. We're just solving the inequality based on the second derivative. So far I've got two possible switching places. I might get another one or two from this, right? Because it could switch when the second derivative is undefined. So here, let's work with this form of the second derivative. A fraction will be undefined when the bottom is 0. So this amounts to figuring out when e to the x squared is 0. But e to a number can never be 0. So this will never happen. So I've only got two possible switching places this time. So then you mark those on a number line. So everything we're doing past this right here isn't calculus. It's just solving an inequality. So just standard procedure for solving an inequality, figure out when your quantity is 0, figure out when your quantity is undefined, mark those points on a number line, then test points, right? Okay, but this time I'm interested in the second derivative, right? Because I'm trying to figure out when the graph of f is concave up. So I care what the second derivative is this time. So I'm going to test my numbers in the second derivative. So the second derivative at, let's try 0 first, that's in here. Second derivative at 0. And again, I could plug it in any form of the second derivative I wanted. I could plug it into here, but I think it's going to be easier to work with non-calculator if I use that form of the second derivative. These are both the second derivative, just written in a different way. This one's easier to work with. So it's negative 2 times 1 minus 0. All over e to the 0, because 0 squared is 0. So that's negative 2 on top over 1, which is negative 2. So that tells us that the second derivative is negative in here. Now I'm going to try something up here. I guess I'll go with 1. That's bigger than the square root of a half. So that's negative 2 times 1 minus 2, because 1 squared is 1. And then 2 times 1 is 2, all over e to the first power, because 1 squared is 1. So that's positive 2 over e. So that's a positive number. So that tells me that the second derivative is positive up there. Okay, then down here, I'll try negative 1. But that turns out to be the same thing. Because negative 1 squared is still 1, right? And negative 1 squared here is still 1. And 2 times 1 is still 2. So that's 2 over e. So the second derivative is positive there. Okay, so the original f is concave up. On what intervals? negative infinity to negative square root of a half, and then also positive square root of a half to infinity. Everybody okay with that? So negative infinity to negative square root of a half, union square root of a half to infinity. That's where f is concave up. And the reason f is concave up there is because the second derivative is positive there. So that's what we wrote down with the concavity test. If the second derivative is positive, then that means the original graph is concave up. Yeah. Yeah. So at the end of class yesterday, I talked about that maybe sometimes you could put brackets in, but that if you left them out, you'd still be saying a true statement. So it's safer to leave them out. And the AP test, as far as I know, gives you credit for the parentheses interval even if there's a bracketed interval that could be. I've seen one multiple choice question once where you had to be able to figure out the bracket, and that's why I mentioned at the end of class yesterday how you would do that. But it's not a big issue. Yeah. So look back at the example yesterday. So if you found out the intervals of increase, decrease for that, the cutoff value would be 0. It's the last example from yesterday. Are you with? So it was just a graph of like, it looked like this at 2. That's the one I'm talking about. Okay, so if you solved this, derivative equal to 0, you'd get as your cutoff point 2. Because the slope is 0 at 2. And then you would test below 2, and you would test above 2. And it would end up being positive on both ends. Because it's increasing on both ends of 2. And so then you would put as your answer, negative infinity to 2, union 2 to infinity. Which would be fine. But we can also tell at the original graph here that it's increasing all the time. Because it's always going up. So it would be okay to include the brackets in this case, in which case the final answer could be this. So here it would be okay to put brackets in. All right, and then on this question, when is the f of x concave down? When is f of x concave down? Yeah, negative square root of a half to positive square root of a half, right? So f is concave down on that interval. Because the second derivative is negative on that interval. Okay, so that was the first part of the question. It said find the intervals of concavity. So we did that. And then it also says identify any inflection points. So inflection points are places where the concavity switches. So based on this chart here, we have a strong suspicion that this is an inflection point because the concavity switches from up to down there. But it can't be an inflection point unless there's a point there. So now to confirm our suspicions, we need to see if this actually outputs a value. So we're going to plug that into f. To see if we actually get a value. So f of x was e to the negative I'm just putting negative square root of a half in for x in my original. And when you square a negative, it's going to come out positive. And when you square a square root, it's going to get rid of the square root. So this is e to the negative 1/2 power, which is the same thing as 1 over the square root of e. Because the half power means square root, and the negative means put it downstairs. Okay, so there is a point there. So now we can say that there's an inflection point there. So officially there's an inflection point when the concavity switches and it's continuous. All right, so there is an inflection point at x equals negative square root of 1/2. And the value is 1 over the square root of e, right? We also have a strong suspicion that there's an inflection point here at positive square root of 1/2, because the concavity switches from negative to positive there. So if we plug that in and get a value, then it will be an inflection point. We just have to double check that. So f of the square root of 1/2 is e to the negative positive square root of 1/2 squared. And that's going to yield the same number. So there's also an inflection point at x equals positive square root of 1/2. Okay, so here's the problem. All of this math that we just did, from that point to this point, looked a lot like stuff you did last night, right? So when you're in the midst of the problem, you're going to forget what you're doing, because it's going to be the same process with the first derivative as with the second derivative. And so you'll get to the end of the inequality and you'll say, wait a minute, did I just do this with the first derivative? Or did I just do this whole thing with the second derivative? Because if you do this whole process with the second derivative, you're figuring out concavity, right? But if you do this whole process with the first derivative, you're figuring out when the f graph is going up as opposed to going down. That's a different concept. So the good news is there's not new algebra to learn, but the bad news is that it looks so similar to the old algebra that you won't be sure which one you're doing. Okay, so what's the method for finding absolute extrema? Closed interval method, right? What's the method for finding intervals of increase, decrease, or local mins or maxes? That's called the first derivative test, right? And then what's the method for finding intervals of concavity or inflection points? Concavity test. And by the way, the concavity test is also what they use in prisons to see if the teeth are bad, right? It's the concavity test.